Hi, this is Larry Feldman with a lesson on arithmetic sequences and series. An arithmetic sequence is nothing more than a list of numbers that are separated by a common difference. So what do I mean by that? Let's do a quick example. Let's say we have 2, 6, 10, and 14. Now, I bet that you can figure out what the next number in this sequence is. You see that the pattern is to add 4 to every number to get to the next number. So 2 plus 4 is 6, 6 plus 4 is 10, etc. 14 plus 4 is 18. Now, the difference between the numbers is called the common difference, and it's represented with the letter D. So D equals 4. And it's important to note that if you take any term and you subtract the previous term, you're going to get D. As long as it's arithmetic. 6 minus 2 is 4. 10 minus 6 is 4, etc. Now, we can model an arithmetic sequence in two main ways. The first way is with an explicit formula that looks like this. A sub n equals A sub m plus D times parentheses n minus m. Now, n and m represent position numbers. So, for example, coming back up here, this is position 1, this is position 2. Actually, let me change colors here. This is position 1, this is position 2, 3, 4, and 5. And n and m, since they are position numbers, must be natural numbers, meaning counting numbers, 1, 2, 3, etc. D is the common difference, and we can use this formula to figure out various terms in the arithmetic sequence. Now, I just want to mention, this is very important. Your teacher may really focus on a variant of this formula, which is this one in green, like that. Now, what your teacher is doing is they're replacing m with 1. Okay? Now this is a valid formula, and it can be very useful. The problem with it is that it can be very limiting. It's only useful if you know or are trying to find a sub 1. If you're trying to find or know any different value, you've got a problem. This formula will probably not suffice. So I would recommend memorizing this formula here and altering n and m to be whatever natural numbers you need. In other words, you could say a sub n equals a sub 2 plus d times n minus 2. Okay, so let's look at this example at the top again. I just want to make sure that it is clear that what we're doing is we are saying a sub 1. That means what is the number in the first position? A sub 1 is 2. A sub 2 is 6. A sub 3 is 10, etc. Now, we can use this formula in a variety of ways, and I want to show you some examples that illustrate just how powerful this formula is. Okay, so let's make a little more room here. And let's do a fairly easy example. Let's say we wanted to find a sub 6. Now, just by looking at this sequence up here, we know that the sixth term would be found by adding 4 to 18. So it should be 22. So can we use this formula to figure that out? And Obviously we can, otherwise I wouldn't be doing this example. What we will do is we will say a sub 6 equals, and here we have a lot of choices. We can use a sub 1, 2, 3, 4, or 5. I just want to show you how versatile it is. Let's choose the second term, a sub 2. We're going to add d times n minus m. Remember, if this is n, this is n. Those must be the same. And if that is m, that is m. Those must be the same. So in this example, n equals 6 and m equals 2. Therefore, in parentheses, we have n minus m, 6 minus 2, which is 4. Let's keep going. A sub 2 we know is here and here. So that's 6 plus 4 times 4, 16. 6 plus 16 is 22. No surprise. Same answer. Okay? So you might be thinking, big deal, Larry. I could have looked at this and told you that a sub 6 was 22 in 2 seconds. But what happens if you're asked to find a sub 100 or something really large like that? Well, let's take a look. Make some room, and let's say you have to find a sub 100. Well, that can be a sub, let's say a sub 3, just for some variety here, plus d times n minus m, that's 97. A sub 3 is 10. We can see that here and here. Plus 4 times 97. That is 10 plus 388. And that is 398. So in this example, you can see that the explicit formula is a lifesaver. It would take a person a long time to figure this out without understanding the formula, but beyond that, really understanding the pattern that exists and why the formula works the way it works. Okay, I cleared much of the screen, and I want to do one more example where we are going to be utilizing much of the information from the example that we've been using. And let's presume that we don't know this value. We know this second value is a 6. We don't know that one. We know the 14, and we don't know the last value. And we're told that this is arithmetic. So how do we solve this? We're going to use our explicit formula like this. And here's a great example of why this formula is superior, in my opinion, to the version that uses a 1 in place of m, because we don't know a sub 1. What we do know, however, is a sub 2. We know that's 6, and we know a sub 4 is 14, right? A sub 2, a sub 4. So why don't we use all of these values in our explicit formula? In other words, we'll say a sub 4 equals a sub 2 plus d, now we don't know d, that's okay, we're going to find it, times n minus m. 4 minus 2, that's 2. By substitution, a sub 4 is 14, right? That's right there. A sub 2 is 6, plus d times 2, I'm just going to write that as 2d, as my handwriting slowly gets worse. 14 minus 6 is 8, equals 2d, therefore d equals 4, which shouldn't be a surprise. We knew that about 10 minutes ago. Now with this d known to be 4. We could use this explicit formula, but now we can just use common sense. This value must be 4 higher than 6, so we know that's 10. This must be 4 higher than 14, so that must be 18. And this value must be 4 less than 6, so that must be 2. Now we're going to talk about the other common way to write an arithmetic sequence, and that is using a recursive formula. And the recursive formula looks like this. A sub n equals a sub n minus 1 plus d. It's much simpler to look at than the explicit formula, but it does have a downside. It's not nearly as useful in general. How does this work? Well, you can start by setting n equal to 2, for example, and I need to backtrack a little bit. You need to set an initial value. So a sub 1 equals 2 in this example, right? A sub 1 equals 2. Now let's set n equal to 2 and sub that in here. So now we're trying to find a sub 2. That must equal a sub what? Well, n is 2. So we sub that in. That becomes 2 minus 1 plus d. And let's presume that we know d is 4 still. Let's simplify. A sub 2 equals a sub 2 minus 1 is 1 plus 4. And notice what we have here. The second term equals the first term plus 4. Well, that shouldn't be a surprise at this point. A sub 2 is equal to a sub 1 plus 4. So that's equal to 6. Right? Now, same formula, different n. A sub 3 must be a sub 2 plus d. Right? We're letting n equal 3 now. If n is 3, we have a 3 here. We have a 3 here. So that becomes, this becomes 3 minus 1, which is 2. Then we add the d. So a sub 3 equals a sub 2, which we just solved previously. That's 6 plus d, which is 4. A sub 3 is 10. So we get the third value. And you keep repeating this algorithm to get successive terms. Now it's much easier and maybe a little bit more intuitive what's going on here. You take a term, you add d to get to the next term. That's how I initially described an arithmetic sequence. The big disadvantage, though, is that if I asked you to find a sub 100, what would happen? A sub 100 equals a sub 99 plus d. What's the problem here? Well, we don't know a sub 99. So we can do this. A sub 99 equals a sub 98 plus 4. And we have another problem because we don't know a sub 98. And that is the big disadvantage with the recursive formula. For large n values, it can be almost unusable, or certainly it's impractical in many cases. So what I covered in part 1, this video, is the topic of arithmetic sequences, and in part 2 we will cover arithmetic series. So I will see you then. Thanks.